Yes.
Okay, so good afternoon, everyone. Thank you for this kind invitation. I emerged from a very intense week, as Kai knows, but I hope I will manage to convey the ideas I have in mind regarding Dropland. It's a sort of jest in names, but as a matter of fact, I'm trying to share with you the main content, the streamline of my ERC, which is called COPMAT, Computation Design of Porous Mesoscale Material. And of course, with an eye on exascale, again, I would have liked to have more time to develop a better focus on exascale, but nevertheless, I hope I will be able to comment a little bit with a very recent simulation we got just last week. Now, coming back to Dropland, I mean, in a sort, again, of jesting mood, I would say, what would the world look like if we could replace molecules with droplets? Of course, it's a kind of exaggeration, but nevertheless, it is no exaggeration to say that there are materials based on soft, exotic states of soft matter, which have new properties. So what kind of droplet-based material can we envisage? And of course, how can we simulate and design and realize them in the lab? And today, again, as I was saying, I will try to give some thoughts on what we can do the day that exascale is with us. So just again, to give the general perspective, soft matter is also called KT physics, nothing is extreme here. So KT is a very small amount of energy. But just because of this, as we know, soft matter has a lot of flexibility, and it's a very fascinating state of matter with lies at the intersection between physics, basic non-equilibrium statistical physics, like namely phenomena like non-equilibrium pattern formation far from equilibrium. It has a lot of numerics, which is the main focus of my talk, namely multi-scale and multi-physics phenomena. The practical implication, as I said, what kind of mesoscale porous materials can we envisage? And from the engineering or applied physics side, I must say that a lot of momentum to this field has been provided by enormous progress in microfluidics, experimental microfluidics. Again, forget about the equation. All I want to say with this slide is that this physics is basically dominated. The difficulty is coming from non-local effects. When I say non-local, I mean that non-linearity due to inertia. These are slow fluids, if you wish. They move very slow, and so the major actor are capillary forces, namely the forces due to surface tension, which keep droplets together. And in particular, for microfluidic experiments, you want droplet to somehow, you want to prevent coalescence, because if you want to generate, for instance, a regular material made of droplets, you want the droplet to preserve their identity and to take a structure in space which is regular, for example. So the danger is that they coalesce. The day they coalesce, you have lost your goal. So again, forget about all these dimensionless parameters. The difficulty, I mean, the numerical complexity is often driven by the fact that these droplets have a size which is fairly comparable to the micro device they are flowing within. Typically, you could think of a droplet around 100 micrometers or 200-300 micrometers, and the channel length, I don't know whether you can see my pointer, HC, is of the order of less than a millimeter. So you have not many rows of flowing droplets, and clearly the confinement has a strong effect on the rheology of these materials. Okay, and of course, it's also something which is hard to compute other than numerically. So just to give you an idea what the soft flowing crystal is, this is a numerical, an experimental work done in Harvard some 15 years ago. And the beauty of this microfluidics experiment is that the handles are simple. Here you have oil, which is this a jet of oil, and you have water coming from up and down, the two blue arrows, and you break up basically the jet of oil. So depending on the flow rate, the brown arrow, depending on the flow rate of the oil, the so-called dispersed phase, and whereas water is the continuous phase, if the inflow of the dispersed phase is relatively low, you have a sort of dilute gas of droplets, the top panel in this picture. And as you increase, in fact, the flow rate of the dispersed phase, you start to generate a sort of, let's call it liquid. There is some disorder and regularity together in the second panel from the bottom. And as you keep increasing the flow rate of the dispersed phase, you start to generate a sort of solid state, first with hexagonal symmetry, the mid panel, and then all of a sudden you have a topology change. There are very interesting dynamical plastic events where topological transition, if you wish, between connectivity 6 to connectivity 3, sort of honeycomb in the fourth panel, in the second panel from the bottom. And finally, if you keep going with increasing the dispersed phase, flow of the dispersed phase, you go to a one-dimensional topology, which is a sort of one-dimensional crystal, if you wish. So the beauty, as I say, is that the experimentalists have a very keen control on these phases. And now think of these droplets as actually the building blocks of a material. For the record, the material is just anti-droplets, because what you would do, you would shine UV light at the outlet of this channel so that the water, which contains some polymers, would crystallize and generate a solid matrix, and you evaporate the oil, so the droplet becomes holes, actually. And if you can control the monodispersity and the regularity of this pattern, what you have generated basically is a material with very regular layout of holes. And this is a lot of application, typically in biomedical application, like, for cell growth, tissue growth, and so on and so forth. But of course, there are many other very intriguing properties. As you know, soft matter is renowned for it's a combination of liquid, gas, and solids, and each of these take liquid and gas like a foam, or liquid and emulsion, like in our case, water and oil. And both water and oil are Newtonian fluids, which means they react linearly to the stress you apply. But as you combine them together, depending on the relative fraction, they behave like anything but a Newtonian flow. And that's very fascinating. And here is just to give an example, if you wish, of the ratio of the amount of dispersed phase that you drive as a function of the pressure. In a Newtonian flow, these two quantities would be on a linear slope. That's what Newtonian fluid is. And as you can see, the emulsion is behaving in a very nonlinear way. It has a 3/4/2 exponent first, and then all of a sudden there is a crisis, and you jump into another branch which has a different slope. Now, the question is, can we actually help the design of this material? Can we understand the rheology of this soft flowing material, and so on and so forth? And let me say that there are, now speaking in terms of computations, continuum methods are, I mean, non-ideal Navier-Stokes equation are hard to solve, just because these fluids are just dominated by the interface. They are very high surface to volume fluids. And atomistic methods typically still are, we don't have enough computational power to resolve, you cannot go to millimeter scale with molecular dynamics. So it looks like a perfect territory for mesoscale methods like lattice-Boltzmann. And I apologize, but I don't put up any slide on lattice-Boltzmann. Of course, I assume that people more or less know what it's all about. It's a minimal form of Boltzmann equation. And if you have questions, I will be more than happy to take them after the workshop is over. The point I want to make, though, is that this physics is basically covering 5 or 6 decades. And the reason is the following. Here is a cartoon, but the cartoon represents the major length scale in play. So you have typically the size of the channel, take a millimeter. You have a droplet diameter d, order 100 micron. And you have, of course, I don't know whether you can see that. I can't see my, okay, here it is, my pointer. And let me cut to the chase. The real difficulty, you have a computer with a given spacing, delta. Okay, when two droplets, like the one here, come to a distance which can easily be below the nanometers, say 10 nanometers, There are additional interaction called dispersion forces, which have various of various nature, could be surfactants, could be just depletion forces, etc., etc. And the point is that these forces are crucial because if they were not around, the droplet would coalesce. And then the whole purpose of the ordeal would be lost because, as I said before, you want to keep the droplets, to keep their own identity. So, and then the problem is already stated because I have a device which is of the order of a millimeter, and we definitely want to help the design, the engineering design. So we want to reach to the millimeter with our simulation, okay? At the same time, the question is, do we need to go down to nanometers and below? Because in fact, we would like to resolve the thin film between the two droplets as they come together. So essentially, you have to go from nanometers to millimeters to make a long story short. And 6 decades, as you know, I mean, there is no way we can, even on the exascale, you cannot simulate 6 decades in 3D, but you probably can in 2D, and I will come to that in the final part of my talk. Now, again, to make a very long story short, what we did, and I regard that as probably so far the most important, the most interesting outcome of the entire project, ERC, there was no lattice Boltzmann which would account with this what we call near contact forces. They take the form of some amplitude times a power of inverse power of the thin film thickness h, and this power typically is 4. So if you only have if you have a negative a in front of this force, you have coalescence, and when the two droplets come together, they merge, and that should not happen. And the question is, how do I implement the situation where when they come close enough, they repel each other so that they can live much longer? So again, in order to save time, the question is, what do I do with the fact that in principle, in order to have a full direct numerical simulation of this phenomena and to have a full direct numerical simulation of the rheology of the materials we intend to design, I should resolve 6 orders of magnitude, and we cannot do that in 3D. So what do? This is very technical, it's about the specific problems of lattice Boltzmann. The only one I want to mention is, because it's relevant, and it's a great gift that there is a number which we can actually trick. And this number is called Kahn number. It's basically the ratio of the interface, you see the orange ring, around the droplet. Lattice Boltzmann, like any other diffuse interface method, has a finite width, which is a few lattice spacings, okay? So you cannot make the interface sharper than that. If you have a delta X of, say, 1 nanometer, you have an interface of 5 nanometers. And in real life, the real droplets, the interface is much thinner than that. It's below the nanometer. So again, I don't give any detail, but the problem we have in principle is that in lattice Boltzmann, the ratio W over D is 3 or 4 orders higher than in real life. And this is a source of worry because when the droplets come together, you don't want any spurious effect. And in principle, you might actually question the entire validity of the simulation, given the fact that you have an anomalous high value of W over D, and this is called Kahn number. I can anticipate the story, and the story is that, happily enough, the Kahn number is, like very often in fluid dynamics, if you have a number which has to be smaller than 1, as soon as it is, say, 0.1, so 1/10, it doesn't really matter if you go from 1 over 10 to 10 to minus 5, because the physics depends analytically on this number. And then your error is in the order of the percent or even less, okay? So that's exactly, let me just give you the bottom line. Of course, that would be very, very long stories, many papers, etc. But the reason why I'm emphasizing this fact that the Kahn number can be tricked is because, and we didn't know that beforehand, it allows us to use much larger delta X. And what most of the work we did so far, unfortunately, if you wish, for this workshop, has does not require an exascale because we could produce a lot of results just using the first strategy of multiscale, namely coarse graining. 3 plus 3 means that I resolve 3 decades in space, and that I can do easily on any computer by direct simulation. And the remaining 3 orders of magnitude, I can coarse grain. I can use some customized lattice Boltzmann, which we developed. And of course, we are making a strong call to universality. And universality means tweaking the Kahn number. And that works. I mean, we have now plenty of evidence that strategy number 1 works for us. And this, I would say, is so far the main result of our ERC. In the beginning, we had something which was much more in the spirit of massively parallel and exascale, which is to say, instead of coarse graining, when I'm in this situation where I have to resolve a thin film, I do local grid refinement, okay? I must tell you that we decided to abandon that because by the time you want to grid refine dynamically, besides being a nightmare in terms of labor, and there are codes around the world, but I mean, it's not easy to learn how to use them. But the real point is that it's very hard to keep the parallel efficiency decent, mainly because of load balancing. If you do, I mean, it's a simple exercise, but you can easily see that when you go really down deep with the grid refinement, down deep means 10 grid refinement levels. 10 levels means 3 orders of that magnitude in space. If you want to refine 2 power 10 is 1,000. So with 10 levels of refinement, you go down by 3 orders of magnitude. And keeping your code efficient, especially in terms of load balance with 10 levels of refinement, is a real nightmare. So in the end, we decided we gave up this. And very recently, and this is work which is still unpublished, I think the exascale really could be a very nice alternative to this idea of grid refinement. Massively parallel means you go DNS all the way. Okay, of course you could coarse grain as much as you can, but wherever you cannot coarse grain, just forget about grid refinement, make a uniform grid everywhere, keep the beauty of lattice Boltzmann. On a uniform grid, lattice Boltzmann gives its best, and go along the exascale road. So I have some application. I don't think I have much time, but I really don't want to insist on that. This is all coarse graining story, beautiful things. I mean, we are studying some exotic state of matters, droplet within droplets, and they dance driven by vorticity, beautiful stuff. But that's not really what I want to focus, because for this workshop, I want to tell you a little bit how we are preparing for the exascale. And then I change. This is a beautiful, I think everybody should agree that this is a beautiful object. It's called Venus basket flowers. This is an animal which lives down deep in the sea, below something around 500 to 1,000 meters. And its amazing structural properties. It's a glass that doesn't break, besides being very, very beautiful. And in a less poetic formulation, you would call it trabecular porous media. And trabecular porous media have a lot of application for regenerative medicine, osteoporosis, etc., etc. So again, it belongs, if you wish, to the category of what I call exotic materials. And I think that's a beautiful picture for an exotic material. And there is a guy in between, which I think is some form of fish, or I don't know the word in English. In Italian is crostaceo, crustus. I don't know. I have to look it up. But you see what it is. So, and I'm proud to say that this is still, we sent this to Nature, and much to our surprise, is a fully computational paper, and they didn't reject. We have 15 pages of question, and we are working out of that, but it is the first time in my life that I don't get rejected, bounce back without referees from Nature with a purely computational paper. Just to give you the idea that just the finding is beautiful. Not only does this beautiful structure reduce drag, which is what you would expect somehow from a porous media, but if you look into these circular vortices inside the structure, and I have a stereo, I must proudly announce that I got this picture 1 hour ago from my group. And unfortunately, I don't have the stereo glasses. They tell me that if you watch this like in a movie theater, it's a rather spectacular picture. But besides stereo effect, the real point is that this vorticity pattern, which you see inside, seemed that it could serve two purposes, namely nourishing the animal, because the animal has to eat something, and also reproduction functions, I mean, of which very little is known. But it's amazing that fluid dynamics can play three roles: reduce drag, which somehow is the least surprising, but probably also feeding the animal and helping with reproduction function. So it's speculation, but it's very well supported by the simulation. Now, coming to the exascale, I said pre-exascale, this is just to give you the numbers, is 50 billion grid points, so it starts to be a serious, very serious simulation. We use about 1/10 of the Marconi 100 GPU-based machine, which is the top 9 in the world, is in Bologna, not far from Rome. And again, to make the long, this is a very highly optimized code. It's plain lattice Boltzmann. There is no nothing near contact forces. This is just a plain lattice Boltzmann with a very, very complex geometry. It took almost 1 year actually to build the geometry one-to-one, because there are textures. I mean, it's a porous medial, very, very sophisticated. And at the end of the day, actually the day means almost 2 years, I must say, the performance is about 3 petaflops, which for about 1/10 of Marconi is pretty good, because Marconi peaks at 32. And as Peter was pointing out early in the afternoon, in this community, we used to measure the performance in loops or mega loops. In our case, we have 15 tera loops. What does it mean? 15 tera loops means that you make 15 updates a second of a cube, which is 4 decades in linear size, namely 10 to power 4 power 3. Okay, you have 4 decades along X, Y, Z. And with this code, you can update such a cube 15th time in a second, which means that if you want to run a single simulation long enough, and with 10 to power 4 per linear dimension, I would say that you need at least 1 million updates. If you do the algebra, it's about 1 day. So 1 day, it's pretty reasonable. I mean, it's something. It's not a month. It's not. I mean, it's absolutely acceptable.
Sorry, about 4 minutes. Yeah.
Okay, but I'm done actually. Thank you. So the point is that actually it's more than I need, because if I want to conclude with what would exascale in Dropland do for us, and of course this is a naive extrapolation, but if I extrapolate, we have a machine now with 32 petaflops, and the performance is good. I mean, it's highly technical, but the parallel performance is on the order of 70% on the 1/10 of the machine. So if I move to exaflop, which is another factor 32, the 15 billion points becomes 1 trillion. But, you know, in 3D, this is no big deal, because 1 trillion means 4 decades. I mean, in scaling up by a factor 32, and the same goes for memory, you scale up a cubic root of 32, which is basically a factor 3 or 4. And so that means that even if you could, and we can't, of course, because there are issues in going to peta to multiple peta to hexa, many issues. But suppose we forget about the issues, we still would need coarse graining. This is the message. We can do 4 decades, maybe a little bit more, but we cannot go from 1 nanometer to 1 millimeter. Definitely, we will not be able to do that, even the day we have the best implementation on the best exascale machine. For this, we need another 3 decades, and that's probably too far, or maybe quantum computing, I don't know. But no, coarse graining is here to stay in 3D Dropland. This is the message. On the other hand, it is true that many of these materials are quasi two-dimensional, like a little bit like in quantum. And in 2 dimension, 1 trillion grid point means 6 decades. So I think that for microfluidics, where again, many materials are quasi 2D, I think exascale will really give access to a situation where you can simulate all the way from the nanometer to the millimeter. So the result is that, again, this is a very audacious, I mean, there are many, many ifs and buts, but let's take a blue sky perspective. In the blue sky perspective, it will be possible with exascale to simulate 2D dropland all the way. And I think this is an exciting prospect. And that's basically all I wanted to say. Thanking again the organizers, and thank you all for your attention. And this is the group, and with a special contribution by Giorgio Martin Falcucci for the Uplectella, for the sponge. And that's basically it. Thank you so much.